We're going to be covering routing basics. We're going to talk about what routing is, how routers make the forwarding decision, as well as the importance of a populated routing table so the routers can make their decision. I've brought up a slide here that shows 6 different routers and a subnet coming off of each router where host computers would be populated. So we might have a machine here, machines in each different area, and each one of these routers might be in a different city. This might be in San Diego, LA. Let me try to think of other areas here. Las Vegas, we could have another one in Las Vegas, St. Louis. So we have some routers, and again, they might be in completely different areas. These are separated by WAN links. Now, the importance of routing is to allow this computer right here to be able to talk to this computer over here. And how does that function? First of all, we need appropriate IP addressing scheme. What we're going to do is we're just going to make it real simple. 192.168.1.1 is this guy's IP, and this guy's IP is 192.168.2.1. Now, for routers to be able to route every different broadcast domain, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 broadcast domains altogether in this scenario. For a router to be able to route, every broadcast domain has to have a unique ID, a unique network or subnet address. I always compare routing to the post office. Every different area designated by the post office needs to have its own zip code. The zip code is what the post offices use to get from one place to another. The routers use network addresses to determine where to forward information. Just like the post office uses a zip code to determine where to forward information, a router will use a network address. Now, to be able to route, let's say this computer right here wants to ping this computer over here. So he types in ping in the command prompt 192.168.2.1. At this point, the computer will compare this IP address to the subnet mask and realize that the network address is 192.168.2.0. That is not the same network address that this guy has. This computer's network address is 192.168.1.1. So he goes, okay, I need to send that to the router. Since it's not within my network, I'm going to send it to the router. How he does that is he ARPs. ARP router, what is your MAC address? The router will have a MAC address on this interface right here. The MAC address might be 9D. So as the computer is addressing the packet, at layer 3, he puts the source and destination IP information. At layer 2, he puts the MAC address information. And what he's going to do is he's going to put the MAC address 9D as the destination, and then he'll put a little trailer on there. He sends it out. The router gets this package and he sees his MAC address, and it's like receiving an envelope with his name on it. What happens when you get an envelope with your name on it? You open it up, and that's exactly what the router does. He strips off this layer 2 information and he looks at the layer 3 addressing, which is the IP stuff. And so he goes, oh, okay, 192.168.2.1, let me check my routing table and see if I have a destination address in my routing table for 192.168.2.1. And he goes, okay, I do. I see it in there. I have to send it out of this interface right here. So what he does is he repackages it at layer 2 to be able to go out of that interface. So a router strips layer 2 frames. It's called a frame when it has this information on there. Strips the layer 2 information off, forwards a packet based on the layer 3 IP address. Before he sends it out of this interface, though, he has to repackage it at layer 2. A typical WAN layer 2 encapsulation is something like PPP. MAC addresses are not needed in this point-to-point serial connection here, so he puts the PPP information on the package, sends it out. This router receives that package, so he sees this package coming in to his interface, and he knows if it's a PPP package, he's got to open it up. So he opens this up, gets rid of the PPP information, and looks at the layer 3 information on here, which is the IP address. And he goes 192.168.2.1. Let me check out what network that's a part of. Oh, that's got to go out of this interface right here. So he goes, okay, let me package that up appropriately. So he repackages it at layer 2. Layer 2 says, here's his IP packet. Hey, you need to get a MAC address. So he'll ARP this computer right here, and his MAC address might be A3. And he says, hey, what's your MAC address? He sends it back A3. So he puts the header information on there, redoes the trailer, sends it out. The computer gets it. He sees his name, strips off the layer 2 information, sees his IP, opens it up further to get to that desired information on the inside of this packet. So routers need to be able to use these network addresses like a zip code, like our post office. First thing they're going to look at is what zip code is this going to, so they know what plane or train or bus, whatever, to put this on. The router looks at the network portion of the address as the zip code, so they know what interface to send it out of. So it's very important that a router knows where these destination networks are located. If they don't, they're not going to be able to send the information. Let's look at how they find out how these destination networks are located. I'm going to bring up a slide here that shows 3 routers: router A, router B, and router C. Now there are 1, 2, 3, 4, 5 subnets in this scenario. Each subnet has to have its own network address. This subnet is 99.8, 99.32, 99.16, 99.40, 99.24. So I've got each subnet with its own individual network or subnet address. But the routing tables here are empty. So let's take a look at what's going to happen with the empty routing table and the importance of having this routing table populated. So I've got a computer over here in the 99.8.0.0 subnet. So here's this guy. He wants to talk to his buddy over here in the 99.24.0.0 subnet. So he wants to send a message to this guy. The routing tables are empty. The IP address for this computer right here is 99.8.0.10. The IP address for his default gateway is 99.8.0.1. And here's the gateway right here, .1. This is the IP address of the gateway, the router's nearest interface. So what he does is he says ping 99.24. Let's say this guy's IP address is .13. So 99.24.0.13. The first thing, again, let me go over this one more time, the router's going to do is find out if this IP address that he's trying to connect to, which is 99.24.0.13, is within his subnet. So he checks this IP address against the subnet mask, which is 255./29.248.0.0, and he realizes something. he realizes that this destination computer is in the 99.24.00 subnet, not in the 99.8.0.0 subnet. So he can't ARP this guy directly and get his MAC address. He's got to send it to the router and let the router take it from there. It's like if I wanted to give mail my next door neighbor a letter, I just walk the letter over there and put it in his mailbox. But if I want to mail something to my mom who lives in a completely different part of the state that I do, I'm going to have to use the postal service because I'm not going to walk there. So he's got to use the router to get the information over to his buddy. So he ARPs his default gateway 99.8.0.1. The router sends back his MAC address. Again, his MAC address might be 9C. And he just sends it back. So he addresses his ping packet IP to the destination MAC address of 9C. Sends it to the router. The router gets the envelope, opens it up, and sees a destination IP address of 99.24.0.13. He goes, hey, where the heck is that? Compares it to the subnet mask and says, all right, that's got to go to the 99.24.0.0 subnet. Let me check my routing table. Uh-oh, my routing table is not populated. I don't see how I can possibly get to 99.24.0.0. My routing table is not telling me anything. Actually, there would be a couple of things in the routing table. His directly connected routes would be in the routing table. 99.32.0.0, directly connected subnets, I should say. So this subnet, 99.32 and 99.8 will be in there because he actually has to, we type in the IPs and the subnet masks on these interfaces and the router does the math and says, okay, I've got these two subnets. Anyway, he looks in there and he sees 99.8 and 99.32, but he does not see 99.24. So what does he do? He gives up. He doesn't try, he just gives up because the routing table doesn't tell him how to get to this destination. So this guy gets very sad because he cannot ping his buddy. Let's take a look at what's going to happen with a populated routing table. I'm going to clean up this slide real quick and populate the routing table. So I've got the routing tables populated here. Don't worry about how they're populated. We'll go into different ways of populating the tables from static routes to routing protocols in other videos. They're just populated. And these are actual RIP costs right here that they're using populated. We use the cost of one router away. Like right here, it's just basically one router away. So what it shows this router now, 99.8.0.0, he knows that his Ethernet 0 interface has a connection to that. We've got serial 0. And Ethernet 0. Alright, so we've got all the routing tables here. They're populated. So let's take a look at the same scenario. This computer tries to talk to his buddy over here with a 99.24 network address. So he ARPs his gateway. This time, when the router sees the 99.24.0.0 destination subnet, he looks in his routing table again, and it says, hey, I have a path to 99.24.0.0. It's right here. It's in the routing table. And it tells him how to get there. It says, you need to go out of your serial 0 interface, and it's 2 routers away. So he goes, okay, I'll package it up to go out my serial 0 interface. So typical WAN encapsulations, PPP. So he takes the IP packet, puts it into a PPP frame, basically packages it up like in an envelope, sends it to router B. Router B opens it up and looks at the IP packet again, does the same thing, says, hey, 99.24.0.0, let me check my routing table. Oh yeah, I've got that in here. It's right here. It's got to go out of my serial 1 interface, and it's 1 router away. So he'll repackage it to go out of a serial 1. Again, maybe PPP or frame relay. Puts it in the PPP envelope. sends it to router C. Router C opens the envelope, looks at the IP packet, and goes, oh, network 9924, let me see. Even though it's directly connected, he still has to check. He goes, yeah, I've got that, 9924.00. That's got to go out of my Ethernet 0 interface, and it's 0 hops away, meaning I'm directly connected to it. That's great. So he packages it up again with layer 2 encapsulation, but this time it's an Ethernet layer 2 encapsulation. So he ARPs this computer right here to get the MAC address, and he puts the MAC address on there. It might be A9 is his MAC address. Sends it out. This computer opens it up and gets the information. If the routing tables were not populated, wouldn't be able to do that. Let's take a look at a scenario where maybe some of the routing tables are populated, but not all of the routing tables are populated. I've cleaned up my slide yet again, and I've made a change here to the routing tables. All the routing tables are populated for A and B, but router C does not have 99.8.0.0. It doesn't have this subnet in it over here. So we've got to figure out what to do, or what's going to happen, even though these routers A and B have all the routes in them. Router C does not. What's going to happen when this guy tries to talk to his buddy? So he sends out his ping. When you ping, you want a response back. You're not just wanting to talk to yourself, you want a reply back. So he sends out his package, and since A and B know where 99.24 is, they keep sending it on. A sends it out serial 0, B sends it out serial 1. C gets it. He knows Ethernet 0. He goes, okay, I'm going to send that package out Ethernet 0. So his buddy sees the ping, and he tries to send a response back so they can talk. When he pings back, however, he goes, okay, 99.8.0.10, this guy's IP, he goes, 99.8.0.10, that's not in my subnet, so I need to send it to my gateway. So he ARPs his gateway. ARP gets the gateway's MAC address, and he goes, okay, I'm sending this to the router. So he packages it up, sends it to the router. The router opens up the envelope, he gets the envelope, opens it up, and sees a destination IP address of 99.8.0.10. He does his math and goes, okay, that's on subnet 99.8.0.0. Let me check my routing table. Let me see, 99.32, 16, 40, 24. And there's nothing in here telling him how to get to 99.8.0.0. You could even have what's called a default route saying, hey, if you don't know where it's at, send it this way. There's nothing like that in there. It's saying, I know where 32 is, 16, 40, and 24. So what's he do? He gives up. He sends a response back, destination unreachable, to this guy right here because he doesn't know how to get there. So this guy gets very sad because he tries to respond to his buddy, and the router doesn't know what to do. So it's important that all of the routers have the routing tables populated. If one of them doesn't, or doesn't know where a particular subnet is, then they will not be able to communicate in both directions. So he's actually receiving the initial ping request or echo request. That's what a ping packet is. It's two parts, echo request, echo reply. He tries to send the echo reply back. This router, router C, can't do it, so they're unable to have communication. So he's getting the hellos, but he's not getting the replies back. I've cleaned up my slide one more time. I want to re-illustrate that point, and I've put the basically what's going to be in the routing tables by default without telling them anything else, by simply configuring an IP address on an interface and putting the subnet mask in there. The router figures out what subnets it's directly connected to. So it knows on the Ethernet 0 interface here, it's got 99.8. and it knows that on serial 0 it's got 9932. Here's serial 0, Ethernet 0, serial 1, serial 0, and Ethernet 0. So again, one more time, if I had a computer here, and let's say from this computer I am simply trying to ping this interface, serial 0 on router B, 99.32.0.2 is the IP. If I try to ping that, again, it's important for all routing tables to be populated for this to function. Because if I send out a hello to that router from this guy, he realizes that 99.32.0.2 is not local, so he packages it up to go to the destination of Ethernet 0 interface on router A. The router opens it, gets the IP packet, and says 99.32.0.2. Let me check my routing table. That's 99.32.0.0 subnet. I've got to send it out of my serial 0 interface, and I'm directly connected to it. So he repackages it with PPP and sends it out. So he puts it in a PPP envelope, sends it out to router B. Router B opens it, looks at the packet, it's for him, he checks it out, a ping, cool. I'm going to ping back. So he sees the destination address that he's supposed to respond to as 99.8.0.10, and he does his math and he goes, oh, that's on the 99.8.0.0 subnet. I better send it somewhere because I don't have that. That's not directly connected to me, so let me check my routing table and see how I can get there. He looks in his routing table. He sees 32. He sees 16. He sees .40. He doesn't see 8. So he cannot respond. So again, the packet can get there, but just because it gets there doesn't mean it can get back. All routing tables need to be populated. If they're not populated appropriately, you're going to have problems. So it's important if you're troubleshooting why this machine can't ping this router over here. Not only do you need to check router A's routing table, you need to check router B's routing table as well. So in this video, we have talked about routing basics, what routing is, how routers make the forwarding decision, and the importance of a populated routing table, and the importance of all routing tables being populated.